Yes, good morning. Thanks for coming. So we are ahead of schedule. And also in my presentation there are no equations. So just some ideas. So the title is extending interval and zonotopic set computation to polytopic set computation for nonlinear discrete-time system. So that's currently I'm working in University of Plymouth, is southwest of UK. I'm sorry. Yeah, the outline is first I will define what means set computation for nonlinear discrete-time systems, and then we just review what traditionally our interval set computation for this kind of system, and what's the zonotopic set computation for nonlinear discrete-time system. So the main focus for this presentation is how to extend the ideas from interval and zonotopic set computation to polytopic set, because polytope is more flexible in shape. So it will bring some flexibility to some control problems. And also I will show some applications of this technique to the control problem, like control invariance or reachable set computation, state estimation as well. So finally, that is the conclusion and the future work. So the first one, what is set computation? Here the set computation I defined for a nonlinear discrete time system. Your current state is here, your next time state is xk. So your input is a set rather than a value. So that is the key for set computation. Your output, xk, or is approximation, is also a set rather than a value. So that is the set computation. So set membership tools. So it's all based on your input is a set, like this here. It can be a non-convex set, any shape of set. It's not a value. So through this dynamic nonlinear discrete time system, we get your output is another set. This set may be more complex, but is your input is a set, your output is a set. Your system here is a nonlinear system. For linear system, that is easier. So we only talk about nonlinear system. So that is our problem configuration, set computation for nonlinear discrete time system. So for interval set computation, I believe that all of us know what this method. So your input is an interval or a box. Your output or is an outer approximation. Usually interval method get outer approximation. Is also an interval and a box. And interval set computation is implemented through the interval arithmetic. So that is the method we all very familiar with. Your input is a box. Your output is, or outer approximation is another box. So your system is nonlinear, and you use interval arithmetic to do all the calculation for the nonlinear system. So that is the way for interval set computation. The power of interval set computation, I think, personally, I believe that we can bisect an interval for a final set computation. If we cannot draw a conclusion about a set property, we can bisect this interval. Look at finer means we look at more detailed one, smaller intervals to get the idea of what these properties are. So we can use bisect and selection, and also we use set inversion via interval analysis. This is the algorithm from Luke Jian's paper. So typically, if we cannot draw any conclusion about this domain, we just bisect it and look at smaller intervals, and then we can draw the conclusion. which this domain is stable or unstable. So that is the power for interval set computation. We can easily bisect an interval and draw a conclusion for a final, and that is the keywords, final set computation. So that is the interval method. I think this is the background. So what I currently want to do is extend all these ideas to be more flexible shape rather than a box or an interval. So that is the background for this research. So extended from interval, there is another method called zonotopic set computation. So this is an existing method that your input is a zonotope. Your output is also a zonotope. Is an outer approximation as well. Is also a zonotope. And the zonotopic set computation for nonlinear system has been implemented via the Coulin's method. You can find this paper, Coulin's method. Basically, in this paper, you can compute the dynamic evolution of a zonotope. For example, for this nonlinear discrete-time system, your input is a zonotope. Your output is also a zonotope. So that is zonotopic set computation. You can say that we extended not I, is Coulin, extended from a box to a more symmetric shape. So this zonotope is a special polytope. Is symmetric. But you can use this method to get an input for this zonotope, to output a zonotope. So that's no problem. So why we use zonotope? Compared to interval set computation, zonotopic set computation can reduce the wrapping effect. I think the main reason for that is that interval set computation usually use the natural inclusion function, where zonotopic set computation use the centered inclusion function. So the details, you can find the literature and to say that why this happened. So here I just provide a comparison between interval set computation and zonotopic set computation. So this is for nonlinear discrete-time system. They start from the same initial state. If we treated this initial state as an interval, we get this third state. This is your dynamic evolution of your system. But if you treated this interval as a zonotope, using the zonotopic set computation method by Coulin, we get this step, the third step. We can say that the wrapping effect is reduced. So here is these are the wrapping effect. So these are all outer approximation. But using zonotope, you get a reduced wrapping effect. That's why there is a lot of research currently using zonotopic set computation for state estimation for many things, because it's reduced the wrapping effect. So that's the definition about zonotopic set computation. As we remembered before, for zonotopic set, we also want to divide the zonotope to say a more finer set computation. So during my PhD study, I proposed a way to how to bisect a zonotope. So now we can also use, like similar to bisect interval, we can bisect a zonotope and to judge the property of this smaller zonotope to get the property of this zonotope. So you can refer this paper to say how to bisect a zonotope. Usually this bisect, because the restriction of the shape is redundant. You can say we bisect this solar tube, we get 2 solar tubes. But this arrow is redundant. It's not like interval. You can bisect very clearly. For solar tube, because the shape of restriction, we can only get this result, the left solar tube, the right solar tube. There are some common errors because for the shape, because after bisect, you want your result is also a solar tube. That's why we get this bisection. What we can use this method, bisection a solar tube. Here is we can test the control invariance. For example, for this solar tube, we computed the dynamic evolution of this solar tube. We find that the next step is not control invariance. But if you bisect it to look at smaller solar tube, we find that every small solar tube, the evolution is inside this original solar tube, which means that this solar tube is control invariance, is based on the set computation. If you bisect this to smaller solar tubes, you can say that this solar tube is control invariance. So use this idea of bisection the solar tube. We can design a control invariant set for nonlinear discrete-time systems. So this control invariance is an important issue in model predictive control or other control. So this set that once you enter this set, your next stage will not escape. You will be always in this zonotopic set. So that is the idea how we can use the bisection to prove something, to prove the control invariance, the idea of this control invariance. So as we can say that we extended the idea of bisection an interval to the bisect solar tube. So that is advantage because we also want a finer set computation to test a smaller solar tube to say what is property. If we cannot draw a calculation for the bigger ones, we can always draw a calculation for smaller ones. So that is the idea for this extension. This is the past work. So the key work here is polytopic set computation. Why? Because after this research, I'm wondering that why we can use input is just a polytope rather than special shape, interval or solar tube. I want my input is also a polytope. The output or outer approximation is also a polytope. So then we can release these restrictions on the initial set. So if we can do that, then that will be a technical advantage there. So this is the idea can be implemented via zonotopic set computation. I will explain how to do this extension. So basically, our target is the input set is a polytope. The system is nonlinear discrete-time system. We want our output is also a polytope. So that is our target. How to do this exactly? Because for nonlinear system, currently there are no method that can do the polytopic set computation. So that is our task to do polytopic set computation for nonlinear discrete-time system. How to do that? That is the procedure. Polytopic set computation can be implemented through zonotopic set computation. The idea is that you first represent this polytope as the intersection of solar tubes. So your polytope will be equal to, for example, for any polytope, you will represent it by an intersection of solar tubes. So you represent this polytope exactly by the intersection of solar tubes. And then the second step that you compute the dynamic evolution of these individual solar tubes. After you compute these individual solar tubes, the dynamic evolution, FZ1. This uses Cohen's method. So then you can calculate FP according to the set 0. It will be equal to this FZ1, 2. So that is the idea, that you can get this exactly polytopic set computation. So I explained the idea here. So first, you have a polytope. You represent it by the intersection of two zonotopes. Then you calculate the zonotopic evolution. You get the intersection here. That is your second step. So your input is a polytope. Your output is also a polytope now. Because use this method, represent this polytope first by the intersection of zonotopes. So that is the idea for polytopic set computation. This we already have some result. And how to do the representation, the first step. How to represent a polytope by the intersection of zonotopes. You can use the vertices of this polytope to construct these individual zonotopes. It can be transferred to a linear program. For example, here, for the blue one, so you for the blue, we have the 3 vertex, like here, the red one. So you can use this linear inequality equations to construct a simple zonotop. That is to contain your polytope. And then you move to another vertex. You can get the green one to intersect. And the final one is here. So you can use this method to use the vertex to get 3 zonotopes. Their intersection will represent this polytope exactly. And also these 3 zonotopes can be optimized to be small as possible. It's a linear a linear program problem that you construct this to contain this original polytope as small as possible. Or you can use randomly linear inequality from this polytope. For example, I use this linear inequality equation. I can construct the red zonotop to contain. I can also use these 2 linear inequality for the polytope to construct. So it's not related to the vertex. So you can use this method to construct the intersection, or use this method to construct interaction. So here I just show that it's feasible, that you can always find a way, a linear program method to construct this intersection, to get represent your polytope by the simple zonotopes. Once you do that, then you can compute the evolution of these individual zonotopes, and then compute the intersection, and then your result a polytope as well. So that is the basic idea. Now, we also want to bisect a polytope, similar to the interval or zonotopic. We want to bisect and to test the smaller zonotop, what the property are. So that is the bisection and selection for final set computation. We think a way to do that. For example, this is your polytope. We can find the Chebyshev center. So any line across this Chebyshev center, we can just bisect this polytope. So Sorry, I just my time is run out. Sorry, I will be quick. We are still schedule. Okay. So we bisect it. We have the left polytope, the right polytope. Use the Chebyshev center to get the bisect polytope, and we can test the smaller polytope, the properties. So that is your left and the right polytope. And then we can develop this set inversion where polytopic set computation. That is, first you bisect, and then you represent this left polytope by the intersection of these three solotopes, and then represent this right polytope as the intersection of two solotopes. After that, you can calculate the dynamic evolution of this left polytope and the dynamics evolution of this right polytope. You can design control invariant polytopic set as well, similar to the zonotopic set. So that is, we extended all the ideas from intervals to polytope now, using the solotope as the medium, the middleman to do that. So that is the idea. So the application can be search inversion, well, polytopic set computation. And also we can compute the reachable set with the initial state of your polytope. So if your initial state is a polytope, you can also compute the evolution of this reachable set. Is always a polytope. This is reachable set computation. And you also do the state estimation. So for every step, you obtain a polytopic set. You calculate this evolution of this polytopic set, and use solotope represent this polytopic set as the intersection of the solotopes. And then we can say every time you get a polytopic set constraint for your state estimation. So that is the application currently I'm thinking of. So conclusion. Polytopic set for nonlinear discrete-time system have certain advantages, as we showed, in terms of accuracy or efficiency for some control problems. And currently I'm developing a dedicated MATLAB toolbox to implement all the algorithms like set inversion where polytopic set, or represent a polytope by the intersection of solotopes. So the standard algorithm is there. Then we can easily plug in your problem to compute the evolution of these polytopes. And more theoretical and practical applications are to be explored for promoting this set membership technique. So it's an idea based on this idea. Okay, thank you very much.
Yes, here you represent a polytope as an intersection of zonotopes.
Yeah.
So I understand this, but why don't you consider instead the union? So that maybe the Z1, Z2, and so on would be smaller, and probably you would have less specificity.
Yeah, you want to hear this way.
It's a possibility. It would be a possibility.
Yes, that will be smaller. Yes, that will be good. But currently, I cannot find a better way to find these smaller ones.
It's difficult.
Yeah, it's difficult. It's like here. If I want to this way, I'm very easy to find this.
Yes, okay, but probably there is some algorithm to find.
Yeah, yeah, that's a good idea because you get smaller solotopes.
Yeah,
but you will need to divide it here in the inside.
Yes. Yes.
Find some.
Probably there exists some algorithm for this. Maybe, I don't know.
Yeah, that's a good idea, indeed.
Yeah.
You get a smaller solotope.
And the thing would be to have non-overlapping zonotopes to be perfect.
It's not possible.
Non-overlapping.
Because the shape restriction.
Yes, probably it's not possible.
I guess it's not possible.
Yeah.
But for the intersection, it's easier. The algorithm, I can easily find these smaller ones.
Okay.
Yeah, good idea. Yes, maybe future.
Can you compute the complementary of the zonotop and then take their intersection against the union of the or the complementary of zonotop and so get the Breuer not convex.
No convex.
Yeah. I mean, take the intersection of the complementary region of all the zonotop. To the complementary region of
This blank region.
complementary region.
Yeah, it's difficult. I think you need, if it's not single ones, it's difficult to get these unions, Yeah, I don't know if there are ways, but these are separate unions. It's difficult to get there. I think the intersection is more, you can easily find more restricted. Sorry, maybe I misunderstand your question.
I just ask how to the idea to compute the union of the.
Yeah, the union, I normally I don't prefer union because union you need to treat every set separately. That's the problem. You need then you get a separated set. Then that will be a problem, The intersection you will always retain a convex set.
Can you do these operations in high dimensions without hitting a combinatorial explosion in the number of vertices or faces?
Yeah, that's a good question. So currently I'm only implanted in 2-dimensional. So the principle, as I explained, like here, you can, like 3 dimension, you can find the simplest zonotope in 3 dimension. Just to find in that dimension your simplest. So the idea can be extended, but the computation will be more extensive.
I wanted to ask regarding to this, what is the computational cost of evaluating the zonotopic function? Is it the same cost as evaluating the box, or is it higher?
Yes, this can be a standard algorithm. Use Coulin's method. So you input a zonotope, you get a.
Yes, but the computational cost of evaluating this function with zonotopes, is it the same as evaluating it with the box, or?
Maybe more extensive. Yeah, but generally it's quick because it's just the equation. Just the equation,
Right.
without internal algorithm.
All right.
Yeah, zonotopic, the paper of Coulin or Span, Alamo. So it's an equation. You just follow these equations. There are no internal algorithm. Yeah.
It's maybe a question about the complexity. Do you know the complexity of the algorithm created the zonotops with respect to the number of vertices, for example, this algorithm? Because you choose 3 vertices and
Yeah.
create 3 zonotops.
Yeah.
It's enough in this case, but you have maybe 100 vertices on your polytop. How many zonotops are you
Yeah.
going to create? And
Yeah. Basically, if you have n vertex,
yes.
you need, if n is even, you need this kind of zonotopes. This is the maximum number you need.
Yeah, of course, but so now about the complexity.
Yeah, I don't have the complexity
Okay.
theoretically. It's just some idea
Okay.
at the moment. Yeah. So basically, if your n is even, you need
Almost.
the maximum.
Okay.
But if you can use 3, 9, you may reduce that number. So in principle, you need n divided by 2. But you can reduce that number based on your special case.
So also, as soon as you compute the dynamical system, you obtain a new polytop and a new polytop and so on. And sometimes, is there an explosion of the number of zonotops that you need during the time?
This one can be explained here, yeah. So usually for the state estimation, you can say that at here, you get a reduced number because your constraint will reduce your vertex.
Or because you have observations.
Yeah. So the better you have observation, you will reduce a lot of vertex.
This was not my question. My question was about the number of zonotopes that you have. At the initial state, you have just one zonotope because it's a regular box.
Yeah.
Then you have maybe two zonotopes needed to represent the top at the first step. But what could happen? Is it possible to have 2 to the n zonotopes?
No, because every time you get a polytope. Okay. So this polytope depends on your problem. So like this way, you have observation, you cut a lot of vertex.
My question is not about observation. It's as soon as you compute, the number of vertices of your polytope may be large or no.
Yeah, depends. What I'm saying is that depends on problem.
Okay.
For some problem, that could be the case.
Okay.
For some problem, the vertex can reduce.
Okay.
So the number of sonotope you needed is purely based on the polytope you get. If you have many vertices, you will need more sonotope.
I understand.
Yeah. So for this case, we need a reduced. So it's not going exponentially or something like that. So it's not appendix your sonotopes. You know what I mean? It's not. It's based on the intersection. Get the polytope. After you get the polytope, you analyze this polytope. So that's the procedure. Yeah. Thanks.
I have a couple of questions related to this. Because you have some techniques that avoid increasing the number of zonotopes. So somehow you can detect that some zonotopes in your, for example, you apply the image, maybe some zonotopes are redundant with the other ones. So we are not participating in the vertices. So you have some techniques to find redundant zonotopes in representation?
Here, the second one, okay. So for any system, for a polytope, you will have like AX.
Yeah.
So you just find the two. C. You just find randomly two inequality. Use this one, you can construct a sonotope.
Yeah, and then you can, when you have,
Until you finish, you use up all the linear equations. So it will not get redundant because you just, like a pool, you just pour two.
Okay, so if you start with, I don't know, 4 zonotopes, you always keep 4 zonotopes throughout all the...
No, it depends on how many linear equality equations in your polytope. So every time you just take out two linear inequality like this one here. So every time you just pull out two linear inequality equations, you use these two linear equations to construct the like here, the red one. We use this line and this line. Then you just discard this. You find a new in this polytope, two new, like here, until you use up all the linear inequality equations. So it's like a pool. You take out two, put other side, until your pool is empty.
Okay, so you pick up all the zonotopes until you have what you
Yeah, you pull out two linear equations out.
Okay.
You construct a sonotope until you finish all this pool. So that's why it's not redundant. But you need, if your n is odd, you need some redundant.
And another question was, is there the other way around? If, for example, you start with a box represented as zonotope,
Yeah.
how do you increase the number of zonotope? How do you obtain polytopes? Maybe I'm missing something. Because if you just apply this computation here, so you have just p equal to z1, you apply one time the function, and you
Yeah.
have the zonotope.
Just one zonotope.
How do you add up new zonotopics to have a real polytopic?
Because for the estimation, you get one solotope, but you propagate, you get a more complex solotope.
Yes, you get a more complex zonotope.
And you have observation, you will then retain a polytope.
By distinction, you mean? Or
No.
observations.
Observations, you will cut some constraint to your.
Okay.
So you will, what essentially you will retain a polytope rather than a solotope.
Okay.
So you need this representation because your target now is not a, for reachable set. If you just from beginning solotope, you go forward.
Okay.
That's okay. You can always use one solotope.
Yeah, of course.
But if you have some intermediate measurement, you need retain a polytope. So that's why I'm promoting the polytopic set computation.
Okay.
Because in some occasions, your set is not a solotope or box. Your set is a polytope. We want to compute the dynamic evolution of this polytope exactly. So that technique can do that. Yeah, thanks.
So,
Okay, thanks.